Hello, linear algebra student. This video is for chapter 4.1, vector space. So this is a new concept. So it is different from what we have done so far. In the past, we have defined what is a vector, right? So it's like an object in space. You can do it as Rn, but vector space here actually more generalized. It doesn't have to be vector in R1, R2, R3, Rn. It's just an objects. So it's a set of objects and we call them vector also. And then we have this concept called space on which we define two operations, addition and multiplication by scalars. Scalars are real number. And then so long as it's satisfied 10 axiom or rules, then we say they are vector space. The good things about like abstractizing some objects into a common name called vector space is um, there are a lot of theorem that we can use to study vector space, like spaces, spanning sets, independence, and all those. So later on, we'll talk about a lot of entities that are, can be classified as vector space, and they would be useful when we study them. So what are the 10 axioms? The 10 axioms are adding. If there's two objects, u and v, in that vector space, and if you add them, there is a definition of adding. And after you add them, they are still in the vector space. And also they're commutative. That means you add a and the u and v is the same as u plus v. It's also associative. If you add u and v first and then add w, is the same as you add v plus w first and then add u. Also, the next one is there is a zero vector. It must belong to the vector space. You can define it what it is so that whenever you use the add some operation to one vector, is this you get the same vector back. Also, there is a negative vector so that when you add to it, it becomes the zero vector. Now, what is a zero vector? Zero vector is such that when you add to something else, get back to that vector. So not necessarily a zero per se, but most of the time it's zero. The scalar multiplication also needs to be defined. So C times U is also in V. And also if we do C, the scalar multiplied by two vector sum is the same as you multiply them individually. And if you have two scalar add first, that's the same as you do individual multiplication also. Yeah, and also if you do multiply first or set or before or after you multiply the vector is the same, and one times your vector is belongs to the same as the vector. So for a for scalar one. So as a result of this axiom, we have three facts also. That is zero actually is a scalar, right? If you multiply by u to u is a zero vector, so you can also generate a zero vector that way. And also C times a zero vector is a zero vector. Negative vector, negative of a vector is negative 1 times the vector. So let's talk about, so of course the O vector that we talked about where entities are line segment in the three-dimensional space are still vectors. Well, actually are vector space. So the way we define those vectors are their arrows, right? They have arrows with length and direction. So we can draw them on space. That's what we defined in the past as a vector. So it start off, at 0, 0, and all those. The length is from 0 to the end of the vector, and the direction is what we talk about direction. We define adding vector by parallelogram law. We also define scalar multiplication by lengthening the vector. So we want to show that this is a vector space that satisfies all 10 axioms. So the first two is we do have the sum, right? So u plus v is defined by the parallelogram law and also the algebraic definition. And because of the algebraic definition of u plus v is equal to u1, so u1 plus v1, u2 plus v2, u3 plus v3. So obviously that would equal to, because of this u and v are real number, so it's equal to u plus v, and also is also associative also. So 1, 2, 3 are all satisfied, right? So axiom 1, 2, 3 are satisfied. So you just need to write down, and because these are real numbers, so all real number will satisfy those rules, right? So real numbers. And then the fourth one is the fact that there is a zero vector. The zero vector, we can define it as negative of u. So for any u, the zero vector 0 is 0, 0, 0. So 0 plus u equal to 0, like that. And also our negative u is negative u1, negative u2, negative u3. So these are defined at 5, right? 4, 5. And so 4 and 5, maximum 4, 5. So to prove something is a vector space, you just have to go through all of them. 6 is if you have any scalar, let C be a scalar, C times U1, U2, U3 would just be CU1, CU2, CU3. After you multiply them, these are still real numbers, so it belongs to V. So it's still in the vector space. So it because we define it by lengthening it. So it is satisfied, 6 satisfied. So this is axiom 6. 7, 8, 9 are 8, 9 axiom would works because if C, D are two different scalar, times U is equal to C du, and also C plus du would equal to Cu plus du as a result of the way we define scalar multiplication. So 7, 8, 9 are all okay, and then 10 would be if I multiply 1 to u, that would equal to u. So because 1 is a scalar, so that's also axiom 10 is also work. So all 10 axiom work, so this is a vector space. The second one we want to talk about is another kind of subjects that is doubly infinite sequence of number. So we write it as yk. So these are like, just sequence of number on the negative side and positive side. We can define them as adding the sequence of numbers. So remember, these are number. Depends on that sequence. Real numbers. And so the sum is defined as adding individual one together. The scalar multiplication is multiplying the C into each individual one. So we have axiom 1, and obviously they are infinite sequence already. So 1 and 6 are done, right? And then we have 0 vectors because the 0 vector is so it would be all 0, right? 0, 0, negative, positive. So this one would be if I have 0 plus a yk, that would still equal to the yk. So that's that and also if I have c, so this is what not 0, right? So 0 add this is equal to this, so that's 4. Axiom 4. I think the most important thing, and axiom 1, 2, 3, and also just the results of adding result of the adding adding the sequences. So because numbers are commutative and associative, so when you add them, they are also adding sequences of numbers inside. So it's very easily proved. Axiom 4 is done. Axiom 5 is I can define something called a negative. So the negative vector would be negative yk is equal to negative u if u is yk, right? So when you add them, that you get 0. So this is axiom 5. Axiom 6, 7, 8 is about scalar multiplication. So we have 6 defined it. 7, 8, 9, 10 are directly a result of you multiply a scalar, C multiplied by yk. You just multiply inside for all of them, C, yk. So this belongs to the vector space also. And then C plus D into yk, we just multiply inside as C plus D of yk, right? So that is also equal to V. So all of these are okay. So all 10 axioms are okay. So if we have any rule that we can use to describe vector space, we can use it to work on infinite sequence. And then infinite sequences are used in discrete time signaling. The third set is we frequently visit in this book, and that is set of polynomials. So polynomials are, a sequence of algebraic expression, and then we have a set of polynomial of degree at most n. And so we with coefficient a1, a0, an. So there's a lot of polynomials in a set like this. So for example, t, 2t squared plus 5, or t cubed plus 2t plus 1. So these are all polynomials. So we can prove that Pn is a vector space by defining if we add two polynomials is as if we are combining like terms. So the whatever combined like terms that we talks about would be the sum of two polynomial, and then C multiply a vector is just distributive properties, distribute into the coefficient. So you can clearly see that axiom 1, 2, 1, 2, 3 follow directly, because when you add them, you can add them in any order you want because of the combined like terms. So this is combined like terms, okay. Axiom 4 is about 0 and negative. So negative p of t would just be negative 1 times p of t, right? And 0 is actually just 0. So 0 is in this space. And finally, the scalar multiplication, Cp of t is also divided as multiply each of the each of the coefficient by c, a1t, all those is also cant, is also in the vector. So all 10 theorem, not theorem, all 10 axioms are satisfied. So we can say that, oh, this is, it forms a vector space. The most important one is actually, the addition and or scalar multiplication. So make sure that when you multiply something, it's still in. And when you add them, they're still in the vector. The next one is the set of real value functions. So we have two real value function as an two object in a vector space. They all have the same domain set D. And if I add them, so I can add the two functions together. That is equal to f of t plus g of t. That is the sum. And I can define c of f of t, cf, they equal to cf. So we can say that these two particular operations, this makes sure that 1, 2, 3 are satisfied. This makes sure that 4 is satisfied, right? But no, this is 5, I think. Is it 5? 5 is satisfied because 5 is the definition of, no, 6 is satisfied. So the definition of the scalar. 6 is satisfied. So it's axiom 6. And then and then we can just need to define what is 0. 0 would just be a 0, f of t equal to 0, right? So it's a constant vector. And then the negative of f of t is just negative 1 times f of t. So all the others are satisfied. So all 10 axioms are fine. So we can say that this sets of all real function in the same domain create a vector space. So you can see to check that something is a vector space, you have to do a lot of work, check all 10 axioms. But to say that something is not a vector space, you just have to point out something that does not work within the 10 axiom. So we'll do the second video in the next video.